She was mentally
Welcome, everyone. I know Francis has so much to say that we need to give him lots of time. My name is Patrice Keat, and I am the co-founder and executive director of the Santa Cruz Children's Museum of Discovery in the Capitol Mall. If you haven't been there, please come. We're open every day of the week, almost every day of the year. And Wednesday is Grandparents' Day, free. And we have lots of interesting activities all the time. So you can take a flyer, go to our website. We're having a big fundraising event on June 8th, a casino night. So if you're on this list, we'll send you some information about that. And we're so excited that you all come, and it's really getting to be fun to see many familiar faces each month. I'd like to introduce Andy Carmen, and he will talk to you for a moment about environteers, and then we'll have Francis Nimmo talk.
Hello. Just to take a few minutes, I wanted to let you know about an important resource in our county, and that is Environteers, and more specifically the website. And wanted to tell you just a little bit about it. First of all, the purpose is to make getting in action to protect and restore the environment, taking action to make it easy for people. I'd say the urgency, but also the enthusiasm for getting involved, participating in direct action is growing. And to make it real easy for people to find events and volunteer opportunities and access all 94 environmental entities in the county, we created this website. I'm going to just show it to you briefly, and then also tell you about the most exciting dang thing in the world, and that is our weekly update. And I'm going to be passing out a sign-up sheet, so if you want, you can sign up and subscribe and receive that. So here's the website, I hope. It's divided according to areas of interest, and within that there's 11 areas of interest, and all the 94 groups are featured there, whether it's oceans or, let's see if I can get to that. And you can see one intent was to make it be attractive here. Sorry, this is awkward to go through when you get onto a photo. I don't know how to undo that.
Press the arrow down keys. It's
There
also.
we go. Anyway, there's areas of interest, and again, all the groups are there with a blurb about them and links to every one of their websites. And then there's events and volunteer opportunities. These are just upcoming events like this talk, films, lectures, fundraisers that are put on by many of the organizations. And then also the upcoming volunteer opportunities in the next month or two. And I wish that would work better, but it's not. Anyway, by event and by calendar, order of appearance, wow, can't do it. But more importantly, you can have access to the benefits of this by just signing up for the newsletter, and that you're going to have trouble reading this from the back, I'm sure, but that once a week I put out a newsletter that has 3 upcoming volunteer opportunities and 3 events. And so you all are on some lists, so you would know about some of these, but I can guarantee you're not hearing about all of them, because they're coming from so many different sources. And we have an initial offer tonight, actually unlimited time offer for free. You can receive this. if it looks appealing, sign up, just put your name and email address, and you'll receive the next one on or about Tuesday. Thank you.
And Andy is the founder of this and has done all the website work and all of the work, so we can thank him for that. I'd love to introduce Francis Nimmo from UCSC, and I can tell that this is going to be it's a popular topic. We're going to learn why Pluto got demoted, I guess, or if. So, and I'm going to let you tell the audience about yourself. Thank you.
Okay, well, thank you very much for showing up. I really appreciate it. Very briefly, I did my undergrad and my Ph.D. at Cambridge in England. And then I spent a little time at Caltech in Pasadena, and I met a girl there, and so then I became very interested in staying in the US, and so fast forward 15 years, and so now I'm a professor at Santa Cruz. And my main interest is in thinking about the insides of planets, how they evolve, what they're like on the inside. And so over the course of my career so far, I've thought about Venus, that was my PhD work, and then Mars, and then I started to move into the icy satellites, and so I became part of the mission to Pluto, which is what I'm going to tell you about this evening. See how that works. There we go. And so this is going to be fairly informal, and so do feel free to stop and ask me questions if there's something I said that you don't understand. It's much more interesting to have a conversation. So this is really a snapshot. This is before and this is after 2015. And so prior to 2015, this is the best image that we had of Pluto. It's taken by Hubble, and you can see it's maybe 6 pixels across. And after 2015, the New Horizons spacecraft sent back these spectacular images. And so basically, Pluto went from being an astronomical object to a world that we could actually think about. And so this is really my story. How did we get from here to there? And then what did we learn? So the first half of the talk is basically going to be a little history of the exploration of the outer solar system. And then the bulk of the talk is what do we now know about Pluto and Charon that we didn't know 4 years ago. So that's the outline. And this is our playing field. This is a picture of the outer solar system. And the outer solar system is very big. You can't really see the orbit of Earth at all. There's Saturn, and then Uranus and Neptune. And Pluto is in this funny inclined orbit. And Pluto is just one member of this family of icy debris, which is called the Kuiper Belt, which is the sort of the outermost part of the solar system. And we'll talk more about the Kuiper Belt later. Question?
The Oort cloud would be that, would it not?
So, okay, the Oort cloud is much further out, and so the Oort cloud basically extends to the next star. And so some material would have been scattered out of the Kuiper Belt into the Oort cloud. That's where some comets come from. But I regard this as the sort of the primordial bits of the solar system that haven't been moved anywhere outwards. But you're right, the Oort cloud is beyond question.
How do you define the Oort cloud, the Kuiper Belt, and the solar system?
So it's sort of fuzzy, but one of the important things about the Kuiper Belt is that most of the Kuiper Belt objects have more or less the same orbit, but then as you move further out, the Oort cloud is actually a sphere, and so objects can come from all directions, whereas in the Kuiper Belt, things are more or less in the same plane.
And the solar system versus the Kuiper Belt?
So in a sense, the Kuiper Belt is just the outer edge of the solar system, and I think I have a plot that will show that later. It's a little more complicated than that because some of these big gas giants moved and they shoved stuff around, so they sort of stirred things up a bit. So I want to go back a little in time because prior to the 1700s, we only knew about the innermost planets. Saturn was the furthest planet that was known to antiquity, but then Herschel discovered Uranus with a telescope. And that's really where the story starts, because after Uranus was observed for a while, it became clear that Uranus's orbit wasn't doing exactly what was expected. There were some residuals. It wasn't where it should have been. And so a couple of people, Leverrier in France and Adams in England, worked on this problem, and both of them suggested that the reason that Uranus wasn't quite where it should be was that there was something further out that was perturbing its orbit. Now, there was a lot of sort of scientific skullduggery that went on, but Leverrier published his results, and Galle in Germany used his prediction of where this new object should be to point his telescope, and within the first hour of observing, he found it. And so that was Neptune. And so, this was a triumph of the Enlightenment, that through pure theory, they had predicted the existence of a new planet, and he went ahead and found it in the first hour. So this was really remarkable. And so people got very excited by this, that you can use theory to predict the existence of new planets. And so people studied Neptune for a while, and then it appeared that Neptune's orbit wasn't quite doing what it was supposed to. And so this became of particular interest to Percival Lowell, who came from a rich family and was basically able to build his own observatory. And one of the things that he was very interested in was trying to find this planet that appeared to be perturbing Neptune. He called it Planet 10, or Planet X, I suppose. And so he spent a lot of time looking for this planet. He never found it, and he also got distracted by the idea of there being canals on Mars, which is now what he's more famous for. He popularized the idea that Mars was an ancient, dying civilization. So there was this idea that there was another planet beyond Neptune, but Lowell never managed to find it. It was eventually found by his successor, Clyde Tombaugh, who basically, he grew up as a Kansas farm boy, and he built his own telescope, and this so impressed Lowell that he was hired onto Lowell's observatory. And in 1930, he found what we now call Pluto, and it's not very obvious, right?
Wow.
There it is there, and there it is there, and so it's moved relative to the background stars, and so it's not a star, it has to be some kind of a planet. When it was found, this created great excitement, and there was an international competition to name this new planet, and it was the winning proposal came from an English schoolgirl. I don't know how old she was, but she must have been about 12, Venetia Burney, and she proposed the name Pluto, presumably because Pluto is the god of the underworld, which is a cold and dark place, like the outer solar system. So, Pluto was discovered. And then, really, for a very long time, nothing happened. And so it wasn't until 1978 that Jim Christie took this not very good image of Pluto. The negative has been flipped, so the Pluto is actually a point of light, but he noticed that the point of light had a bump on it, and that bump appeared and disappeared, and that became obvious that this was a moon of Pluto, so it was called Charon. And so now Pluto has its own little comparison. Some people pronounce it Charon because that was apparently the name of his wife. And the interesting thing about Pluto and Charon, I don't know whether this will work, let's try it. There we go. So Charon always points the same face towards Pluto, just like our moon does. But Pluto itself always points the same face towards Charon. And so as they orbit each other, they're locked, and so they're always presenting the same face to each other. And that's what happens, that's the final state that the Earth will be in. After a few extra billion years, the Earth will be presenting the same face towards the moon all the time. It just hasn't happened yet.
Is the orbit circling?
Aha! So, as far as we can tell, there was a period when people thought that Charon's orbit might be slightly non-circular, which would be very interesting because that would provide a heat source, but that I think has gone away.
Why is that the Earth is not rotating at one point?
Do you mean why?
Yeah, like this.
So what's happening is that the tides that the moon raises on the Earth are slowing the Earth down, and the Earth is slowing down, the spin of the Earth is slowing down measurably, and it will spin down and down and down until it's always presenting the same face to the moon. It hasn't happened yet because the rate of the spin slowing is small.
What slowed down Pluto?
The same thing, except it's not tides of an ocean, but you get solid body tides too. It gets flexed, and that dissipates energy, and that causes it to slow down.
Maybe we could just say that in equilibrium, the two of them rotate as a rigid body.
Yeah, that's right. It's as if there was a bar joining them, and they just go around in a circle. That's right.
The moon must go much faster than Pluto.
Our moon?
The Pluto's moon must go much faster in its rotation to keep
So,
the same phase.
The way to think about it is that it's this period of the spin and the period of the orbit are the same. And so as it's turning, it's also moving around in the orbit. That's the way to think about it.
But Pluto is rotating, and so is its moon.
Yep.
And its moon is rotating much faster.
No,
No.
no. They're both rotating at the same period, which is the orbital period.
All right.
Imagine if the bar joining them,
All right,
they
all
rotate
right.
as a rigid body.
Wait, are we saying rotation is the same as revolution?
Yep, yep. The spin period and the orbital period are the same for both bodies.
Faster velocity.
So,
So our moon at one time, when it was formed, presumably was spinning.
it will have spun down to this synchronous really fast, but the interesting thing is that the Earth was spinning extremely fast when it formed. The Earth was probably spinning, the day back when the Earth formed was probably 4 hours. So it was spinning extremely fast, and it's been slowing down ever since. Okay, so one of the things that was not immediately obvious was how big Pluto was. And when it was discovered, people thought that it was kind of the size of the Earth. That was the idea. But this is a plot of how estimates of its mass changed as a function of time. And you can see that after a couple of decades, people decided, well, maybe it was the size of the Mars, or maybe it's only the size of the Moon. And you can see that if you project this down far enough, then Pluto will have disappeared altogether. But this is the right number. Pluto is very small. It's a few thousandths of the mass of the Earth. And as I'll show you, we didn't actually know exactly how big it was until really very recently. Okay. Things really kicked off in 1989. 1989 was important because that was the year that Voyager 2, which is this very long-lived spacecraft, flew past Neptune and Triton. And Triton is the big moon of Neptune. And the interesting thing about Triton is that it probably started out life as a Kuiper Belt object like Pluto, but then it got captured by Neptune. And so in a sense, Voyager 2 gave us the first look at what a Kuiper Belt object might be like. And so that really sparked people's interest in what the Kuiper Belt was like. And so a group of planetary scientists who called themselves the Pluto Underground started to lobby for a mission to Pluto. And the US Post Office got in on the act in 1991, where they produced a set of stamps for all the different planets, and for Pluto, all they could say is not yet explored. So people started to design a mission that would go to Pluto and then carry on to another Kuiper Belt object. And missions are enormously expensive and time-consuming, and like all big projects, they go hugely over budget, and in the end, NASA got fed up and said, we're going to cancel this. And so in 2000, it was cancelled, and so it was back to the drawing board. And this was the era when the NASA administration were trying to do things in a sort of competitive framework, and so they actually had a competition. They said, give us your ideas and we'll pick a winner and we'll give them $800 million to build a spacecraft. And so The first competition was held in 2000, and a mission to Pluto called New Horizons was selected. And so this is when things really started to happen, because it was approved and people started to spend money and build spacecraft. And the fact that it got selected is really down to this guy, Alan Stern, the principal investigator, the PI. He has essentially devoted his entire career to making a mission to Pluto happen. And if you ever meet him, you will recognize he's a pretty formidable individual. I would not mess with him personally. And so, by the time I joined the team in 2014 or thereabouts, he'd been working on this for 25 years. And at one of the meetings, he handed out these tiny little stubs of pencils. What on earth is this? And apparently this is his way of reminding you to be persistent, that you keep scribbling and you scribble and you scribble and you scribble until only the nub of the pencil is left. So that's his sort of trademark. The other thing that happened is that, in the 25 years that he was working on getting this mission going, academic historians actually started writing papers about how do you get a mission going, because it's not a simple process. There's politics involved, there's technology. And so this is a scholarly endeavor in its own right, understanding how missions get selected. Okay, so this is what the spacecraft looks like. The details don't matter too much. The most important instrument by far is LORRI, which is really a very, very good sort of telescope camera. You can see that you have a very big radio antenna because Pluto is a long way away, and so it's hard to transmit signals back to the Earth. And then this thing hidden at the back is in some sense the most important bit of the spacecraft. It's a lump of plutonium because there's not very much sunlight at 40 AU, and so you have to power the spacecraft somehow, and you do it with a lump of plutonium. And so getting permission to launch a lump of plutonium on a rocket is quite a large undertaking in its own right.
How much?
Oh, I don't remember, but several kilograms. So.
Are there dangers involved? Why is it a big deal?
Because plutonium is very dangerous stuff. That it's poisonous as well as being radioactive, and so you really don't want the rocket to blow up and smear plutonium dust all over the atmosphere. And so you have to really convince people that something bad is not going to happen, and you have to convince the lawyers that it's okay. So getting permission to launch is really very difficult.
And our inventory is not very big.
Correct. Also, we don't have that much plutonium.
Couldn't you just explain that it would be better to get it away from the Earth?
That's not what they're worried about. They're worried about it coming back.
I understand.
Yeah.
Does the environmentalists on Pluto object to that?
So no, but there is somebody in the NASA organization called the Planetary Protection Officer, and her job is to make sure that you don't contaminate the other planets. And so, for instance, if you send a spacecraft to Europa, you have to be extremely careful that the spacecraft can't possibly crash into Europa and contaminate it. And so that, again, that adds complexity and expense, because we don't want to go contaminating other planets.
Well, you're sending uranium
Yep.
to Pluto.
Yep.
You can't help it for it to be there.
But it's not going to land. If it lands on Pluto, that would be bad. If it's in space, that's okay.
Okay.
Well, it's not going to be a big deal. And in any case, it's plutonium-238, which is not fissile. So the aliens couldn't build a bomb out of it.
This is true. So this is what the spacecraft looked like. You can see the radio antenna, which is sheathed in what looks very much like gold foil. You can also see it's not actually that big. I mean, it's the size of a big SUV, say. And then here it is at launch. It was traveling. It went past the moon's orbit in 9 hours, so that's moving. But it's a long way to the outer solar system, and so it launched in 2006. By 2007, it was going past Jupiter, but then it was going to take 8 years to get to Pluto. And so that's a long time. And so what they did was they basically put the spacecraft into hibernation. They woke it up once a year to make sure that it was still okay, and then they put it back to sleep again. Okay, meanwhile on Earth, things were happening. And in particular, it became very obvious that there were lots of interesting objects in the Kuiper Belt. Pluto was just the first one that was discovered, but there were lots of things out there. And this character in particular, Mike Brown at Caltech, threw a spanner into the works by finding objects that were bigger than Pluto. And in particular, he found Eris, which, as far as we can tell, is about the same size as Pluto, if not slightly bigger. And he found a bunch of other small objects too, but it was Eris that really caused the problem, because if Pluto is a planet, then Eris has to also be a planet. And so then you start to think, well, how many planets are out there? Because I don't want to have to go learning the names of 30 or 40 or 50 planets. And so this precipitated a bit of a crisis. And as you probably all know, the IAU, the International Astronomical Union, they decided to redefine a planet in a way that Pluto was no longer a planet. So this was very sad. And it even created protests. It's a little hard to imagine this is real, but, and it also created some pretty spectacular cartoons. I particularly like this one. This is from XKCD. I don't know if you know it, but it ends up with, "I stand by what I say, Pluto should never have been a planet." So, Pluto was demoted, but it's still interesting. One of the things that happened is that New Horizons flew past Jupiter. Here's its trajectory. And this was actually a very good time to turn it on and to test to make sure that all the instruments were working. And so this was duly done. And what it did was it captured several spectacular images of Io, which is a moon of Jupiter, erupting. So Io is so close to Jupiter that the tides cause it to heat up to the extent that it has enormous volcanoes. All these orange dots are volcanoes erupting on the dark side of Io. They're glowing, and you can see here's one that's erupting on the limb, there's another one, and there's another one. So this was a good test of...
What are the 3 photos?
So those are different bands. So this is optical, and then MVIC and LISA. LISA is infrared, and MVIC I think is UV. So they're just different wavelengths. Question?
I forgot, what was the reason of why they determined that Pluto is not part of our family anymore?
So, what they did was they defined the planet in 3 ways: that it orbits the sun, that's fine; that it's round, that's fine; and then that it's cleared the environment around it. And that was where Pluto lost out, because there are lots of Kuiper Belt objects, and the space has not been cleared. And so that was the definition. Now, people argue vehemently about whether this is a good definition, but that's the definition.
That was also true of Eris.
Yep. Yeah. So none of the objects that we know about in the Kuiper Belt are planets.
But Neptune doesn't clear its orbit.
Well, this is why it's a bad definition. And then let me just show this to you. So this is a not very good movie, but you can see it's actually erupting. You can actually see the plume. So there you are. You have an eruption in action.
How high is it?
It's about 200 or 300 kilometers high, so it's high. Stuff is coming out really fast. And so then it was basically the long haul out from Jupiter to Pluto itself, and this was what was going to happen during the encounter. So this is the plane of Charon's orbit, and so New Horizons was going to come through in between Charon and Pluto, and then as soon as it got past, it was going to turn around and look back towards the Earth, which allowed you to do clever things to probe Pluto's atmosphere. So it was and the whole thing, you can see, the whole encounter was only going to take a few hours. So after almost 10 years of waiting, the whole encounter was over like that. And so you had to make really sure that everything was going to work. Okay, so as July approached, images of Pluto taken by the spacecraft started to get better and better, and you couldn't really do anything with these. But one thing that you could do was to, you could look for hazards. Oops. So we knew that Pluto had little moons as well as a big moon. So this is Pluto, there's Charon going around it. But you could also look for where there was other debris, because you don't want your spacecraft traveling really fast to run into a lump of something, because that would be the end of the mission. When we got our first good look at Charon, we saw straight away that Charon had a strange dark spot at its north pole. And so that was an early discovery before we got good images. And so people started to think about why that might be. And like I said, it was important to get images to make sure there was nothing in the space that the spacecraft was going to fly through, because you don't want to run into it. I mean, in fact, there was a whole sort of contingency plan that if we did spot a ring of debris or something like that, the safest place to fly past Pluto is actually as close to Pluto as you dare, because Pluto has an atmosphere, and the atmosphere will sweep all the debris away. And so if there was a ring of debris, we would have changed course and gone right next to Pluto, which would have been pretty exciting, but also pretty scary. As it turned out, there was no debris, and so the course was kept the same. And so here we are, 11 days out. And then, on the 4th of July, when everybody was at a barbecue, the spacecraft computer crashed. And so a lot of people got hauled out of their barbecues and put to work, and fortunately it wasn't a very big problem, and so by the 6th of July, everything was back on track, and that's the PI and that's the project scientist both wearing spacecraft hats. And so they were back in business. Here we are, 7 days out, 3 days out, and now you can start to actually see things that look like geological features. That looks like it might be some kind of impact crater. Maybe that's another one. And then 2 days out, and this was the last thing we saw before the actual encounter day. And you can just see this bright spot just starting to come into view. And so here we are, 1 a.m. on the encounter day. You can see happy scientists looking at images, and that's the first image we got. There's that bright spot that I'll talk about more later. That was the original image. You can do some fancy image processing to sharpen it up, and then you can overlay color on top of it at 3:30 in the morning, and so then you're ready for your press conference. And one of the interesting things about this mission was that it attracted various hangers-on, and my favorite hanger-on is Brian May, who in a previous life was an astrophysicist before he went off to play the lead guitar for Queen. So there you go. More happy scientists looking at the new images. And so these are the kind of images that they saw. This is a particularly beautiful shot. This is the bright area on the left, and then you can see the sun is low in the sky, and so the mountains are casting shadows on the area beyond. And I'll talk a bit more about what all this means in a minute.
What's the scale?
So this area here is about 100 kilometers across. So these are sizable mountains. These are several kilometers high.
Damn good picture.
It's a very good picture.
Can't see the polar bears on the ice floes.
No, but you'll see interesting things. I'll show you in a little bit. And so by chance, this happened essentially 50 years, more or less to the day, after the first ever spacecraft pictures were returned from Mars. And so in some sense, these two events bookend the first 50 years of space exploration. And one of the really striking things to me is that there are people who were involved in this spacecraft mission who are still scientifically active now. And so that's pretty impressive. All right, so summarize, this is Pluto before 2015. This is Pluto after. The post office were good enough to update their publicity. And so that's the first half, and in a minute I'm going to ask, well, what do we learn from all this? But if you want to take a couple of minutes break, that might be a good idea. Get upstairs, and you can ask questions. I might have a coffee.
So what is your
So up to now, this has basically been history. What I'm going to try and go into now is a bit more about the science, what we learned. And so one thing I can do is to sort of place Pluto and Charon in context. And so this is just a rogues gallery of most of the icy bodies with the Earth's moon for scale. So Jupiter has 4 big moons, Saturn has Titan, and then a bunch of little moons. Uranus has 4 moons, Neptune has Triton, and then there's Pluto and Charon. And so we expect these objects to have some similarities. And so the kind of questions that we want to ask in general are, from my point of view, there are really 2 questions. First of all, what are these things like on the inside? And in particular, people are very interested in whether these icy bodies have oceans underneath, because then they start to think about, whales. And then the other question is how they formed, so what were their starting conditions, and then you really want to be able to join the dots between what they started out like and what their structures are like today. And so you also want to think about how they got from the beginning to the present day structure. So these are the kinds of questions that we want to try and answer. And prior to New Horizons, we really didn't know very much about Pluto. We were pretty sure that it was icy, but the density told us it had to have some kind of rock on the inside. We knew that it had an atmosphere, and the atmosphere was actually a bit annoying because it meant it was very hard to tell Pluto's size accurately because the atmosphere kept getting in the way. And then spectroscopy told us that it has nitrogen ices and methane on the surface, but we had no idea what it actually looked like. So I'm going to take you through all these in detail, but I'm going to sort of start by summarizing what we learned. And the first thing we learned is how big Pluto is, because we didn't know that precisely before. One of the big surprises is that Pluto has an active surface. There are bits of Pluto, the surface of Pluto, that are extremely young, and that was a complete surprise. I don't think anybody really expected that. Furthermore, the surface and the atmosphere appear to be coupled in the same way that the water on the Earth is coupled to the atmosphere. There seems to be a cycle, it's just with nitrogen rather than with water. Almost certainly, Pluto has a subsurface ocean, so, yay whales. And then Charon probably had an ocean, but that ocean didn't survive to the present day. And so these, from my point of view, are the sort of big 5 takeaway points. And so what I'm going to do now is I'm just going to step through each one in turn. So, as I said, because Pluto has an atmosphere, from Earth you can't tell precisely how big it is. You can tell to within, 30 or 40 kilometers, but you don't really have a precise measurement. And so when you have a spacecraft, this is pretty simple. You take an image, you know the scale of the image, you measure Pluto with a ruler, and you get a size. Now, in detail, it's slightly complicated, more complicated than that, but not very. And so now we know the radius of Pluto to a couple of kilometers, and the radius of Charon. And the real importance of that is that it tells you how dense Pluto is, which was not well known before, and so that tells you, to some extent, what it's made of. The other thing that we looked for is that if a body is spinning fast, it's going to be fatter around the equator, like many of us. But to the level that we could measure it, neither Pluto nor Charon had any kind of a bulge. All right, so what? Well, this is a plot of the densities of Kuiper belt objects as a function of their size by Mike Brown. And what you can see is that Pluto had a really big error bar. It could have been as dense as Triton, or it could have been as dense as Charon. And so, this was an annoyingly large uncertainty. And what the New Horizons mission did was it basically removed those error bars. And so now we have a really very precise measurement of Pluto's density. And one of the interesting things that you can see in this plot is that small Kuiper belt objects are low density and big Kuiper belt objects are high density. And that's probably just because the big ones, the pressures are large, and so any sort of pore space gets squeezed out, whereas the small ones just have lots of voids inside. And so this trend with size is probably understood. The other interesting thing is that we can now say definitively that Pluto and Charon really are different in density, and so that means they're made up of different stuff. And so that's actually really important, because that helps you to understand how they formed.
Or could Pluto just be squeezed more under gravity?
So it certainly is, but this effect is much too large to be explained. I mean, that is an important effect, but it's important at the less than 1% level, so you can't just explain it that way. But that's certainly an effect you have to take into account. So there are basically two models for how Pluto and Charon formed. One is rather like the way our own moon is thought to form, that basically something large smacked into Pluto and knocked a chunk off that eventually became Charon. So this is the giant impact model of formation. The other possibility is what's called pebble accretion, and the picture there is that you just had a huge cloud of pebble-like objects that gradually collapsed and happened to collapse into two objects, Pluto and Charon, rather than a single object. Now, the important point about pebble accretion is that if you're just making things out of a bunch of pebbles, the two objects should be the same. And what our results are telling us is that they're not the same. And so now that we have a precise measurement for the density, that really favors the giant impact model and not the pebble accretion model. And so just by getting that precise density, you can tell something about how these objects formed.
But you're assuming that the pebbles are homogeneous.
Well, what I'm really assuming is that if there are enough pebbles, then on average, you'll make both things out of the same. So it's a statistical argument.
One of the last slides was density in the Kuiper belt.
Mm-hmm.
And Charon and Pluto, you had a lot of variation,
Yep.
but the others didn't show any variation.
So, right, there's a lot of variability in here, and so, I mean, what's special about Pluto and Charon is that we're pretty sure they formed in the same neighborhood. You might imagine that there are sort of variations in whatever the pebbles are made out of on large length scales. But I agree that, you know, some of these variations are really very big. I mean,
Eris.
Eris in particular, that's a weird looking object. The Haumea, more recent measurements have moved this down, but Eris looks peculiar. And so I think there are probably other things going on, particularly with Eris. So it's not, so pebble accretion certainly can't explain all this diversity.
I hate to break your train of thought, but those Kuiper belt objects, I'm kind of curious to know how they're pronounced. Would you mind just?
So I can do
You
some.
don't have to do that now, but if.
So I can do some of them. Some of them are impossible. There's Quao War, which you'll see later. I do have a slide right at the end with some of the more exotic ones. This is, again, Mike Brown is mostly responsible for these names. So the geologists were very interested, and so as geologists do, what they tried to do was to map different regions of Pluto. We only saw about half the planet, and so over here you can't really tell what's going on, but half of the planet was imaged very clearly, and so you can see that there's an enormous amount of diversity. Also, if you look carefully, you can see that the naming convention is interesting. So for instance, these Terra regions are all named after explorers. Pioneer, Hayabusa is a Japanese spacecraft, Venera is Russian, Voyager, Viking, and so on. So the naming convention is kind of fun. And of course, we got spectacular images like this. This is false color. This isn't real. And very oddly, north is to the right for some reason. But the point is that you get truly spectacular images of the surface. And in particular, this region, which is called Sputnik Planitia, after another explorer, turned out to be extremely interesting. And this is a close-up of it. And you look at this, and it looks kind of wrinkly, but the point is that there is not a single impact crater. And so that has to mean that this is a really young surface, really geologically young. It's probably less than a few million years old. And so that was a huge surprise.
Was New Horizon detecting a magnetic field, like iron core, maybe geological?
It looked for one and it didn't find one. And so as far as we can tell, there's no dynamo like on the Earth. But that was certainly something that people were thinking about. So one way of thinking about it is that this is what a typical icy satellite surface looks like. It's got craters all over the place, and if you compare it, this is at the same scale, and if you compare it with this, there are no impact craters at all. So this area of Pluto is geologically active.
Are those sand dunes or what?
So we think that they are, so this is, it turns out this is nitrogen. This is a plane of solid nitrogen. And so these little spots are where the nitrogen is subliming away. It's evaporating into space. And so this is driven, we think, by solar heating.
What are those contracts?
These things. So I'll get to that. Okay, so here's Sputnik Planitia again. And one thing it's important to realize is that this low, flat plane, this is all solid nitrogen ice. The mountains on the side are water ice. And so water ice is like rock. Solid nitrogen, it turns out, is really soft. It can actually flow. So this is almost like, you know, a lake, except it's solid, with rigid mountains around it. And the car tracks, here they are again. And what you can see is that this is in the nitrogen plains. And so they outline cells. And so, you know, as soon as you see this, you think, I've seen that before. And what everybody was thinking about was pictures like this. This is probably golden syrup, and it's convecting. So you have rising cells and sinking cells. The white is where the fluid's rising, and the dark is where it's sinking. And so this is what convection looks like viewed from the top. And so we think what's happening is that the nitrogen is soft enough that it's actually flowing. It's rising up and going across and then sinking down. And so it's that overturning that's making this surface so young. It's in motion, it's just too slow for us to actually see it.
And what would power each of these convections?
Okay, so I'll talk about this a little more in a sec, but basically the inside of Pluto is rock. Rock has radioactive material decays, and so there's heat coming out of the inside, and that heat is enough to drive this rather sluggish convection. And that's because nitrogen is really very soft. It doesn't take much force to get it to move. And in fact, this is a simulation of one of these rising convection cells, and then there's a sinking one. And the horizontal length scale is about right. And it only needs to be a few kilometers thick. And so this is the picture, that this is actively overturning on a time scale of hundreds of thousands of years. Something else that was completely unexpected. And so here the color is elevation, and so this is low, and here are the high mountains. And what you see is if you zoom in, you can see this feature here, which I've blown up here, and that is a glacier, right? It's obviously a glacier. It's cutting through the mountains, it's got dividing lines. And so this is a glacier of solid nitrogen. And so what seems to be happening is that the nitrogen must snow out or precipitate out on the highlands, and then it collects into glaciers, and then the glaciers flow down into the nitrogen lowlands. And so you've got this cycle, just like on the Earth, except it's nitrogen, not water. And there's another example. Look at that. It's actually curving around before coming out.
What's the temperature there?
So the surface temperature is about 40 Kelvin, which is right at the point where nitrogen goes from solid to gas. And so you just have to heat it up a tiny bit and it will sublime. And the reason that it's pinned at that temperature is because it takes energy to do that, and so it sort of gets stuck right at that transition point.
What's the tripping point?
Oh, it's not much warmer, but it's at higher pressures. And so you might get liquid nitrogen a few kilometers down if you can warm it up a bit. We don't know that that's happening, but that's a possibility.
In Fahrenheit, what is it?
Oh, I have no idea. 40 Kelvin is really cold. It's got to be like minus 300 Fahrenheit or something. It's really cold. I mean, it's minus 220 centigrade. It's really cold. Something else that we saw was extensional fractures, faults, and so these are a bit like the faults that you might see in the basin and range. These long linear features, they show vertical offsets of several kilometers, they extend for hundreds of kilometers. You can see in some cases they actually cut through craters, and so it looks like the whole surface is being slowly pulled apart. This is a bit more contentious. I'm not sure I actually believe this, but some people say, well, you know, this is elevation. You have a mountain with a hole in the middle, and on the Earth, we call a mountain with a hole in the middle a volcano, right? And so people think that maybe there's sort of cold volcanism, maybe it's liquid methane or something coming out of the surface. I would think we really don't know. I mean, this is a very peculiar feature. I'm not sure I would want to say it was a cryovolcano, but it's certainly a mountain with a hole in the middle. This is one of the most spectacular images. This is taken after going past Pluto, looking back, and because of the sun, you can see that there are all these lovely haze layers in the atmosphere, right? And you can also see the shadows that the mountains are casting, and then this low region is Sputnik Planitia, the nitrogen plains, and so this is just illustrating that maybe there really is this nitrogen cycle, that it goes off from the plains, it precipitates out on the mountains, and it returns as glaciers. And so this was a complete surprise. Nobody expected this. Coming back to something we talked about earlier, this is a close-up of the nitrogen plains, and these things were nicknamed bacilli because they look like, you know, little bacteria on a petri dish. They're holes in the nitrogen plains. And we really don't know what they are, but most likely they're caused by sunlight evaporating the nitrogen off, and there's some kind of feedback. You know, maybe once you've dug a hole, you concentrate the sunlight, and so more of it comes off. And we've actually seen things a bit like this on Mars. This is the polar cap of Mars, and this area is called the Swiss cheese terrain because that's what it looks like. And that really is, that's sublimation. This is the sunlight causing evaporation and making these holes. And so maybe what we're seeing on Pluto is something analogous to the Martian polar caps. Something else that we saw are called blades for obvious regions. This is in the highland region, and you can see there are these sort of ridges that are maybe a kilometer high and tens of kilometers long. And again, nobody really knows what these are, but most likely these are giant versions of this. These things, you find them in arid mountain regions on Earth. They're called penitentes. And again, they're a product of sublimation and feedbacks. And so you get these really bizarre spire-like ridges, and maybe these blades are giant versions of this process. And so there's all kinds of weird and unexpected stuff. Okay. Enough about the surface. What about the inside? Well, one of the big questions was whether or not Pluto has an ocean. And so this is a question we actually thought about before we got to New Horizons, before we got to Pluto. And so this is just a model. So this is distance from the center, and this is time. And so you have a rock core on the inside and ice on the outside. And what happens is that as time proceeds, the rock heats up. That's the warm colors because of radioactive decay. And so the heat then escapes out into the ice, and so the ice warms up, and after about a few 100 million years, you put enough heat into the ice that it starts to melt, and you form an ocean. And you can form an ocean a few 100 kilometers thick, and then as the radioactives get used up, the ocean starts to refreeze. But what this is showing you is that from a theoretical point of view, there's no difficulty with having an ocean on Pluto. There's enough heat produced by radioactive decay on the inside to maintain an ocean for billions of years.
That 200-kilometer thick ocean.
Yep.
That's a lot of pressure.
Yep.
Can you have one of the other forms of water or ice?
So that's an excellent question. And as far as we can tell, you don't have any of the high pressure phases of ice, because if you do, then as that phase grows, you'll get contraction. and we don't see any evidence for contraction. What we see evidence for is expansion. And so that basically rules out high pressure phase of ice. I'll talk about that a bit more in a second. But it's certainly something that people thought about. So this logic is all very well, but there's a problem. And the problem is that if you allow the ice mantle to convect, it removes heat more effectively. And if it removes heat effectively enough, then you never develop an ocean. And so if the ice mantle is static, you get an ocean. If the ice mantle can convect, you don't get an ocean. And so from a theoretical point of view, you can't tell which of these is going to be the right answer. And so an ocean is permissible, but it's not required. So much for theory.
In the solar nebula,
Yep.
it's assumed that the radioactive materials were evenly distributed with regards to distance from the sun.
It is, and so we're basically assuming that the rocks that make up Pluto are the same as the kind of rocks that we find in the asteroid belt, and that's an assumption. It's hard to see what else we could do, and there are good reasons for assuming that the solar nebula was pretty well mixed, but it is an assumption. If there's much less radioactives in the outer solar system, this could be wrong.
How do you think the boundary between the rock core and the ice mantle?
So this was done before we had the new numbers, but it turns out we guessed luckily, and so you just do it based on the bulk density. That tells you how much rock there is. Okay, well, we can think about what evidence would there be for an ocean. And one is that if the ice shell gets thicker, then you get extension. And the reason for that is very simple, that ice is less dense than water. And so as you convert water to ice, the total volume expands, and you're sitting on a sphere, and so the outer part of the shell has to move outwards, but because you're doing that on the sphere, if you move outwards, you're going to stretch, and so you get extension. And so just the refreezing of an ocean is going to give you global extension, and that's exactly what we saw with all those fractures. And so that seemed like a good test. Something else that happens is that not only does the ice shell thicken outwards, but it also presses down on the water underneath, and so the water gets pressurized, and if it gets too pressurized, it'll shoot out to the top, and so that's a good way of generating cryovolcanism, if you happen to believe in cryovolcanoes.
Shoot out against gravity.
Yep.
But wait a minute, water is pretty frozen at that temperature.
Well, so the ice shell is a nice insulator, and so that's the point of the modeling, that it's not too, as long as you've got some heat source inside, you can keep the water liquid for a really long time. And then the third thing is that if you ever develop an ocean, then Pluto's ability to maintain an ancient bulge goes away. The bulge will just collapse. And so these are three observational consequences of having an ocean. There's the bulge collapsing.
Why does it collapse?
Basically because the shell isn't strong enough on its own to maintain that shape. And so if you decouple the shell from the rigid rock, the bulge just collapses because the shell isn't strong
You
enough.
know the spin rate, so we should be able to compute the shape of the geoid.
That's right, but there are other objects where they've frozen in a shape that was formed when the thing was spinning much faster, like our own moon. Our own moon has this shape memory of when it was spinning much faster. Pluto doesn't seem to have that. So we certainly see surface extension. If you believe in cryovolcanism, we see cryovolcanoes, and we didn't see any sign of a bulge. And so none of these are bulletproof, but you've got these three lines of evidence that suggest that there probably is an ocean. And so Pluto is an ocean world, just like Europa and like Titan and like Enceladus. And so in my view, Pluto is an ocean world. We're not as confident as compared to somewhere like Europa, but it seems to me the circumstantial evidence is quite strong. Okay.
Is the ocean salty?
We don't know, but most likely it is, just because the water will have circulated through the rock to some extent, and as it does so, it will have picked up salts from the rock. And so for the place where we know best is Enceladus, because we've got samples of the ocean, and there it is quite salty. And so by analogy, we'd expect Pluto's ocean to be quite salty too.
Could volcanoes have to be linked to some kind of tectonics? And could this cryovolcano be more like a big geyser?
So I think volcanoes and tectonics are very closely linked because you need to have some kind of fracture that gets through the ice shell, and so the best way to do that is by some kind of tectonic event. So I think they're very closely related. But if you have tectonics, that doesn't necessarily mean that you have to also have volcanoes. You can have tectonics without volcanoes. Although I don't think we have any examples of that. All right, well, Charon, I think, gets unjustly ignored. It's not as interesting as Pluto, but it has some interesting aspects. And one is that, just like Charon, there are these enormous fractures. Just like Pluto, there are these enormous fractures on Charon. There are some little fractures down here. But then this thing is a giant rift valley. You can see that there are the flanks of the rift valley fault several kilometers high. And in some ways, it looks a bit like, say, Valles Marineris on Mars. So this is a gigantic set of rift valleys, a bit like the rift valleys that we see on Mars. So Charon has also been tectonically active in the past, and we can even work out roughly how much it's stretched. And so we thought about whether Charon might also have an ocean. And so this is showing a comparison between Pluto and Charon. So there's Pluto's ocean persisting to the present day. Charon probably had enough heat just about to melt a thin ocean, but because it's so much smaller, it got rid of its heat too effectively, and so the ocean died. And so we don't expect Charon to have an ocean at the present day, but it's quite likely that it had an ocean in the past. And so Pluto is an ocean world. Charon may have been an ocean world once upon a time.
There's some boundary between the liquid ocean and solid ice at something like 0 Celsius, but under pressure it's not the same.
No, that's right. It changes, but it doesn't change a huge amount. And so actually what we were more concerned about is that you can imagine that there might be antifreeze in the ocean. Ammonia, it turns out, is a very good antifreeze. And so if you want to stick some ammonia in the ocean, it makes it much harder to freeze. And so this is the most pessimistic case. If you add ammonia, it's much easier to sustain an ocean. And so here we were being as conservative as possible. Okay, so here's what we learned. We learned its size, it's active, there's probably this link between the surface and the atmosphere. Pluto is probably an ocean world, and Charon may have been an ocean world once upon a time. And of course, there's a lot of other stuff that I didn't have time to talk about. So one common question is Pluto active? And in a sense, it certainly is, right? This area, Sputnik Planitia, is definitely active. But that doesn't necessarily mean that it's active on the inside. It might be dead on the inside, like our moon. It's active on the surface because there's this transfer between the atmosphere and the surface and back again. There's no sort of direct evidence for internal activity, and at least on most of the ocean worlds, the thing that drives the activity is tides. Pluto doesn't really experience tides, and so you wouldn't expect it to be active. It's not like Io. All right, so I'm sort of circling back to the beginning. We asked about the internal structures, and in particular, Pluto, I think, probably does have an internal ocean. Charon might have done once upon a time. It doesn't now. In terms of their formation, it really seems like the density argument favors the giant impact hypothesis. And then in terms of evolution...
The library closes in 20 minutes. If you need a library card, please go to service desk now. The restrooms will be locked 10 minutes before closing. If you need to print or make copies, please do so now. La biblioteca cerrará en 20 minutos. Si necesitas una tarjeta de biblioteca, por favor visita el escritorio de servicio ahora. Los baños estarán cerrados en 10 minutos. Si necesitas imprimir o hacer copias, por favor hazlo ahora.
All right. So they formed an ocean. The ocean slowly cooled and refreezed, maybe generating extension and cryovolcanism. And then there's this active interchange between the surface and the atmosphere. Here's a spectacular picture with the shadows cast by the mountains and the hazes in the background.
Oh, slow down.
Questions?
No, slow down.
are the mountains just big chunks of ice that have been pushed around and there's
Yep.
nothing folded or?
As far as we can tell, they're big chunks of ice. Now, a good question is, why is Sputnik Planitia there? What's that low plane doing? And when you don't have any other idea of what to do, you appeal to an impact. And so most likely, Sputnik Planitia is the hole that was left by a giant impact that then got filled in by the nitrogen ice flowing downhill. And so the mountains around the edge may have been caused by that impact event. That seems pretty reasonable.
Oh, I'm just curious, what is the atmospheric pressure on Pluto, and is it sufficient enough to affect any of the surface features?
So the atmospheric pressure is like a millionth of the Earth's, so it's very, very thin, but I mean it's enough for, if it plates out over tens of thousands of years, you can actually accumulate enough stuff to form these glaciers. So I think the way to think about it is timescales are very long, but you can do geological work.
Snow, sun, wind, that can blow it away.
Yep.
What was the imagined estimated thickness of the gaseous region? I mean, salt, the ice of whatever form versus rock.
So probably the solid ice is about 100 miles thick, and then you've got about 100 miles of ocean, and then you've got about nearly 1,000 miles of rock. So Pluto is more rock than ice, and you can tell that from the density.
So under that pressure, do we have the other forms of ice?
So no, the pressures aren't quite, they're sort of right on the edge, but from the observations you don't see any compression, and so that leads us to think that you're at shallow enough pressures that you never get this transformation into the higher pressure ice phases.
The picture of Charon showed a lot of impact craters.
Yep.
Do we believe that those impact objects on Charon and those that came to the Earth and the inner planets, pretty much the same material?
Almost certainly, most of the things that hit Pluto are icy objects, are comets. On the Earth, we were hit by a mixture of comets and asteroids, and it was probably more asteroids than comets. So the mixture is very different. On the Earth, we were mostly hit by rocky things. Out in the outer solar system, we were probably hit by things that were significantly icy.
And so much of it hit the Earth early where it was became our water, our oceans?
Some of it, I mean, that's...
But that may or may not have happened on Pluto.
Right, Pluto was probably, I mean, Pluto has a lot more water, relatively speaking, than the Earth does. The Earth is extremely dry. If you think about, how thick the oceans are compared to, right? And so the Earth probably got its water from comets, but it doesn't have much water compared to Pluto.
So what's the evidence that radioactivity is the cause of heating in the Earth and other bodies? And then two, how would the solar system accumulate enough uranium from supernovae?
So, I don't know much about the original production of the radioactive elements, but the best way we have of estimating how much radioactive material is just by measuring the meteorites that look very primitive, they haven't been processed, and you can figure out, how much uranium and thorium, potassium there is relative to the major elements. And so we assume that the Earth is made up of more or less the same stuff, and in fact, there are some samples from the Earth's mantle that sort of confirm that. And so we have a pretty good idea of how much radioactive material there is in the Earth. And the Japanese in particular are using geoneutrinos to actually measure that directly. You can use geoneutrinos to measure how much radioactive potassium there is. And so that's a direct measurement. It's a hard measurement.
But how would it accumulate enough from supernova dust from...
I mean, that I don't know, but if you measure the meteorites, you can tell how much is in there. So that's a measurement.
Interesting, thank you.
Why aren't there distinct shadows on the far distant mountains on this side the way they are in the foreground?
So that's a very good question. I think the way to think about it is that, you can see where the shadow is, and so the things that are closest to this is the terminator, where you don't get illuminated by the sun. So the closer to the terminator you are, the longer your shadows are. As you move in this direction, the sun is sort of more overhead, and so what you're seeing is the geometry of where you are with respect to the sun.
That's an
In other
incredible
words,
picture.
It's an incredible picture.
In other words, what looks there like a very slowly curving surface is actually curving
Yeah.
more than we're seeing.
Absolutely. Going from here to here, you're going some fraction of the way around the globe. Yeah.
Are those artifacts, those parallel
These
lines?
stripes, yes, I don't think those are real, because this is dark, so there's no signal. Let me just wrap up. So obviously you have a perfectly functional spacecraft. It's just gone by Pluto. You're not going to turn it off, and so what you do is you look for another target. And it turned out this was actually much harder than anybody expected, and so a fairly large chunk of Hubble time was burned up looking for a follow-on target. And in the end, we found 2 Kuiper Belt objects that were accessible. And so there's Pluto, and then there's the target, MU69. And on January the 1st of this year, we flew by a small Kuiper Belt object. And so this is nicknamed Ultima Thule. This is Ultima, that's Thule. And you can see it's really 2 objects smushed together. And so this is what would be called a contact binary. It's a binary where the 2 things have actually hit each other. And so it's not actually a huge surprise, because we visited comets before. Some comets come from the Kuiper Belt, and comets also appear to be contact binaries. This is CG67. And so binaries, contact binaries, appear to be extremely common in the outer solar system, and that for sure is telling you something about how these things formed in the first place. So, right, this has been cooked because it's gone close to the sun, and so if you take this and you bake it, you probably end up with something like that. Ice.
That image right there came shortly after the flyby, and we were told to expect much finer resolution, but we never saw it. And I'm not complaining, that's incredible.
Yep.
But what happened to the extra resolution?
So they're not much better than this. So there are images that are slightly sharper, but there aren't going to be any super close-ups. I'm not sure that's true. The problem is that you're so far away that it takes a really long time for everything to come back, and so not everything has come back yet. And so I don't know what's waiting in the buffer.
That's 1/5,000th as much sunlight as we get, or 1/500th, something, some tiny fraction.
It's a tiny fraction, so it's like it's 1/3000th or something like that. So it's very dim out there.
They're not sending the entire image at once, they're breaking it up.
It's not that, it's just that they took a lot of images, partly because you didn't know exactly where this thing was in the sky, and so you had to take images sort of to both sides of it to make sure that you caught it. I think there are some higher res images too, but they haven't come down yet. There's a lot of stuff to come down, and it takes time. I can skip this. All right, so let me wrap up. I don't think anybody expected to see anything like what we actually saw. People will claim that they predicted things, but I think no. Prediction is hard. The universe is much better at creating interesting looking things than our imagination is able to produce. And so, again and again, we've seen things that we simply didn't expect, and I think Pluto just proves that. The other takeaway is that one person can make a huge difference. If you think about Alan Stern, I mean, it took him his entire career, but he basically single-handedly got his spacecraft to Pluto, and that's a huge achievement. And then the last thing is that the outer solar system isn't that far away, and there's a lot of interesting stuff out here. And so here are some of these very weird names. There's Hua-Wo, Maki-Maki, Sedna, Haumea we know has moons, Eris has a moon, and so there are plenty of interesting targets to look at. And so I think studying the outer solar system has a bright future as long as we have the will to do it. And so I will leave it there. Thank you.
I would like to remind people that we have forms over there we'd like you to fill out about, so we get feedback. What did you learn? And also what else you would like us to present. And we have books here. And then Next month, we will have Ron Duncan, who is the general manager of the Soquel Creek Water District, and he'll be talking about the science behind our local water. So we hope to see you then. Thank you so much.
Tremendous.